So good afternoon, ladies and gentlemen. Excellencies, first of all, let me thank you very much, the organizers, and in particular, Michael Fauland, for this very, very nice invitation to come here to talk about innovation, new solutions. I know that you are economists and nanotechnologists, but I think we very well complement. And also, let me say that the two sessions that we had already, which touched on the green transition technologies, were very professional, and I tried to really continue from that where we left. My talk today is really more on technologies, and I try to show you some of the solutions which actually are there, that's the state of the art, but also try to show you what's behind the corner. Because the future looks much brighter than you might think in terms of innovation and in terms of technologies. There's a range of new technologies coming over a certain timeline. Which are very promising and may be, of course, part of the large solution on carbon decarbonization. I will also touch about some of the mechanisms that we need to push these new technologies forward. But I will start with the big frame. Let's frame the question about technologies in terms of the challenges that we have. I think when the historians, after some few centuries, define this century, they will define it as a century of climate change and sustainability. This is the century of climate change and definitely sustainability. And the whole century will, in some way, be characterized by these themes. It's important also to recognize that climate change, climate action is part of the larger sustainable development goals. And let's not forget those as well. There's poverty, education, water, etc. Climate change is for sure linked to many of those. But in terms of policies, we should keep in mind this broader picture. So the SDG, 17 goals, let's keep those in mind when we go further with the new technologies. The challenge that we have in front of us is shown here. The emissions, if we would not do anything, as the Georgieva IMF boss showed us, will lead us to a catastrophe. So the upgoing curve indeed will cause ecosystem damages from which the planet most likely will not recover. The Paris goals are clear where to go in order to reach sustainability by 2050, 2060, middle of the century. The emissions should be in balance with the sinks. So we should be at a so-called carbon neutrality level, as you sure know. Now, the challenge is that the emissions have not come down. The challenges are maybe leveling out, but the emissions increase with the economy. So when we have economic growth, the emissions increase. And the reason is very simple, because most of the energy, 80% of the energy, is still fossil fuel-based. And it has been for the last 20 years. So we haven't seen any radical change in that. And now there's the big question, when would the emissions globally start to come down? If we want to keep on the pace of the Paris Climate Agreement, the emissions should reduce by the end of this decade by 40%. 40% globally is a huge challenge, but that is the path that we have to take. And then, as said, by the 2050, 2060, we would reach then carbon neutrality. This is perhaps the largest quest that the mankind have ever had, and indeed should be taken very, very seriously. There's many effects of course, from the climate change and climate change mitigation. Economic effects, it will be, of course, a major investment, 2 to 3% of the GDP. So you can understand much of the economic growth may go into the investment for the future. But also there will be stranded assets from the fossil fuels, which will not be used. 80% of coal would need to remain unused, 30–40% of the gas and oil. And that's definitely a major political question as well. So not a simple question globally. The blueprint for going to carbon neutrality is clear. Even though we have problems in order to do that, but it's clear what to do. And the International Energy Agency just recently issued the last plan how to reach carbon neutrality by 2050. There's 4 major pillars in that. The first is that the energy system. The energy system constitutes about 60% of all the greenhouse gas emissions. So we need to do something with the energy systems. Those have to be net emission based by 2050, that is carbon neutral. And you see here on the right-hand side also how to do that. Clean electricity will be very important. All in all, electricity of the final energy uses will be the most important. The electricity use, as we have heard before, will increase quite much by the middle of the century, at least doubling, maybe tripling. Also, we have to change the fuels from the present fuels into alternative fuels, clean fuels, and to electrification. So e-mobility will be extremely important. Those are clear messages, and there's a lot of technologies to do that. But in addition to that, we need to look on other things like also other greenhouse gas emissions. Now we're focusing very often on CO2, which is important, but we have forgotten that 30% of the greenhouse emissions are methane emissions. So methane leakages and how we cultivate our agriculture in future may be important. You will see now that actually climate change mitigation goes also to other sectors, not just the energy sector. But maybe the most important two remaining pillars are, first of all, energy efficiency, or let's say efficient use of energy, in the sense that you get more with less. I think economists must like that. You get more with less, but that is for energy is really the key point. IEA estimates that about 40% of all emissions reductions come from energy efficiency. Energy efficiency, energy savings, as EU say, comes first. Then you can start to think about supply options. So the saved energy is much more precious than the spending energy. Now, having done all these tricks, the question is, would that be enough? Unfortunately not anymore, as the emissions are not coming down yet. And we would need carbon management. So we have to remove carbon from the atmosphere or from our fossil fuel plants and store that underground. Carbon management becomes increasingly important the more we go closer to 2040, 2050. And that's something to start to anticipate about. So indeed, this is the major blueprint for how to reduce emissions to the Paris Agreement goals. You may imagine that all the sectors of the society will be affected by climate change mitigation, and it doesn't leave anybody cold, so to say. And that's why I think it may be better also to characterize the energy transition as more as a societal transition, like the Industrial Revolution. And indeed, when we think about the measures being now technologies, I focus on those today, but let's not forget that the societal impacts and also the social impacts are very important, not to speak about the economic impacts. So we could think about the transition more as a clockwork, which has gears. And all the gears have to move in a synchronous way that the clock goes forward. If, for instance, most of the population resists the transition, you don't have acceptance, it stops, we can't do anything. So the social issues, as we heard in the last panel, will be more important. Socially just transition is important. So very often the energy transition links maybe your mind to changing your technology and another one. It's not enough. You have to look on the whole picture on the societal change, and that makes the whole transition even more complicated. The European Academy is here some time ago when giving advice to the commissioners, pointed out that yes, this is a systemic change, so you need to look on the whole picture. Questions like the carbon pricing, as we heard from the managing director of IMF, carbon pricing is one of the most important actually measures which leading climate economists of Europe advise. Also, the fact, a certain technology diversity will be necessary, as we will see later, in the sense that all countries in Europe, at least, are very heterogeneous. You have different backgrounds, and one solution may not fit all countries. So technology diversity, carbon pricing may be key issues that we need also to keep in mind in this talk. So where do Europe stand in terms of climate change mitigation, and I also taking into the picture the energy security? Well, we have done much, but there's still very much to be done. Let's not forget that around 70% of all energy in Europe is still fossil fuel. Remember, globally, it's 80%, 70%. All the red colors here are fossil fuels. And just before the crisis, energy crisis, 60% of our energy was imported, the highest of any continent. US is energy independent, basically. China also almost. And that energy dependency caused the energy crisis. So we have shot ourselves in our foot that we didn't actually take seriously energy security 10, 20 years ago when the first signals came there. And now when we speak about climate change mitigation, of course, we have to look on both issues. Unfortunately, the measures, being energy efficiency or clean energy solutions, work in the direction that security improves and the emissions reduce. So of course, the EU programs now, the updated programs, the Green Deal with the REU Power and Fit for 55 and so on programs are very important now in the context to really divert Europe from the fossil fuel path to a clean power path. But again, you see that the challenges are huge. It's also important to point out that the member states that we have in Europe don't stand at the same standing point. So if you think about the climate change mitigation as a marathon, some of the countries are 10 kilometers off before the race is starting. And the reason is that of course, if you look on the carbon intensity of the countries here, which is shown by the blue color, or on the wealth of the countries shown by green, they differ very much among European countries. Very often northern countries, or those countries with hydropower or with large bioenergy resources, already a century ago actually started to use those. And they didn't know anything about climate change. I think about Central European countries, their indigenous resource in energy was fossil fuel, very often coal, and they used that. And now when we start to reduce emissions, you can imagine those countries who had bioenergy or hydropower by chance. They are well off already in climate change mitigation without doing anything. So those countries on the left-hand side, they have to do much more than those countries on the right-hand side of the picture. And you can imagine that we need climate solidarity within Europe in order in some way to be able to incorporate the different measures and technologies to reduce emissions. This is, of course, a major political question, and I think for sure also a very important question. Can we succeed with the climate change mitigation? Now there comes the question, where is the globe going with the investments in terms of reducing carbon emissions? We know that the carbon emissions, they are leveling out. We don't yet know when they start to turn down. They should do it already. And these are very bad news. But the good news, very good news, is that the markets have changed very much. Actually, last year, if you look on all energy investments globally, the majority of all investments went to clean energy. Renewables surpassed the investments in fossil fuels. 60% of all investment goes now to clean energy. And that's important to recognize, of course, that we can't change what we did in the past, but we can change now the future by doing now. And that's why these investments that are increasing. You see the green columns with renewables, they are increasing, energy efficiency increasing, grid investments increasing, a very important infrastructure investment to enable use of renewables or any clean power technologies. All those are increasing. So altogether, this would be a very, very positive signal. Energy crisis and the COVID-19 aftermath have also increased investments, in particular in Europe. Last year, 30 to 50% increase in renewable energy investments, and that will continue most likely this year. Energy efficiency improving. So these big crises that we have had here around the last years have in some way perhaps changed the pace also to introduce better the new technologies. Importantly to emphasize is also that, well, we put a certain percentage of GNP into change. But I'm a believer of the Schumpeterian creative destruction, in the sense that now when we destruct those fossil fuel industries, the clean energy will actually create more new industries, and the numbers support that. We have already close to 30 million jobs in renewable energy only. And I'm not accounting for energy storage or energy efficiency, which is millions on the top of that. And we start to be in a point where we have more working places in clean energy than in the fossil fuel energy. So it means that this transition will also create jobs and welfare, which is extremely important for the societal impact and also for the economy. And here we see also for the different technologies how those jobs are now split. Solar energy, wind energy, for instance, quite important. Now you may ask yourself, why are we investing already so much in renewables and in new technologies? Are there maybe subsidies so much that it spurs these investments? And the question is actually, it's now the market mechanisms that take care of the growth of the new technologies. In this figure, you see different recent statistics on the price of electricity produced by different technologies. And in most of the figures that we have nowadays shows that wind and solar, those, as an example, the newest technologies, are actually already competitive based on the price of electricity that they produce. In particular, on the right-hand side, you see with the latest numbers, which show that solar wind would be cheaper than fossil fuel electricity production. So then the question is that, well, should I invest to dirty, more expensive energy, or clean, cheaper energy? And I think the markets make a correct conclusion. We invest more into clean and cheaper energy. If this development goes on, and let's just look on the right-hand figure here, let's assume that things go well, and the prices are at the level that we have here. International Energy Agency estimates that by 2050, a critical year for carbon neutrality, up to 70% of all electricity globally would be solar and wind. And you see here a clear change away from the fossil fuel production into renewable production. We will need, of course, other technologies as well, but these are one of the mainstream lines that we have here. Also, technologies like hydrogen are starting to appear in the scenarios by 2050. Hydrogen, an important energy storage by a fuel, which we can make by electricity, and energy efficiency definitely also part of that. And also CCS comes there already. So it's like a fruit salad. You have a range of technologies, and this of course causes some challenges. As you know, solar and wind are weather-based technologies. It's not a fuel. And now the question is that if we have so much wind and solar, have IEA made some mistake? Because, I mean, we have to live also in the night when there's no solar, and also live when there's no wind. And here comes a very important point later on here is that actually, in addition to wind and solar, we have also to look on flexibility, infrastructures. So fuel, that is very good. You can regulate your power system based on demand. But weather, you can't do it. But if you add flexibility to weather, so weather plus flexibility start to be like a fuel in the power system. Now, before going more into technical details, let's take something that may be important for the audience. You are economists here, and let me just take a few slides also and comments on the market acceleration, which is necessary. Even the numbers look very good. These are very promising numbers. We need to easily triple, quadruple the amount of new technologies on the market. So the very good signals and market news are not enough, and we need indeed to accelerate. Market signals, that's what we need. In some of the technologies which are there, we don't have market signals enough. For instance, for flexibility, energy storage. There's no market signals for energy storage, even though we know that, well, we will need that. And that, in that sense, the policymaker should be more alert on that. And thinking about the energy transition and technologies, how to speed now. Now, you have, now simplifying very much, you have two types of measures which you can use. You have the technology push, which is R&D, development, piloting, and then you have the market pull, which are, for instance, I would not call subsidies, but let's say learning investments. You really pull the market with some kind of support. If you've been successful in combining market pull and technology push, you come to a positive vicious circle where the price comes down, increase the market, which again decreases the price, which gives you again new energy markets. And in that sense happens a major global penetration. We've seen this with batteries. We've seen that with photovoltaics, that the clever use of this mechanism can be very efficient economically and leads to major market penetration. And indeed, when we speak about the global energy system change, you have to think really about the economic efficiency. I think the price of the energy what these technologies produce is a very important factor to think about when we look on investments because of the huge magnitude of the investment. We speak of trillions now instead of billions when we look on the energy change, technology change globally. Funding energy R&D, well, when I speak of technologies, that is important in the sense that the technology push activities are still very important. You have to do some improvements in technologies, and indeed that requires some R&D funding. We have, of course, public funding on R&D, but even more importantly, which has been forgotten, is of course the corporate R&D funding. Corporate R&D funding is about 3 times higher than the public funding. If we take the European funding on public funding on R&D, that's the bottom figure here, shows that we put most of our funding in energy efficiency, then comes nuclear, and then slightly less on renewables. That's how we invest in Europe, our R&D funding, and it's on a long term, of course, R&D. And the corporate funding goes to more short term, very important technology development which you need to do in order to bridge the technology and the market. And that's very surprising there. Most of the funding goes actually, or the corporate funds goes to mobility, electric vehicles and batteries. That's the bulk of the investment, and less on the supply side, which is surprising. I mean, we're talking about energy, but still the energy supply side gets much less than the automotive side. So thinking about now the large energy transition, most likely we should have a lot of solutions coming up, or European solutions coming up also on the transport sector. Globally looking on this investment, it's a pity that these emerging economies, they invest very little in R&D, even though we know that more than half of all investments have to take place there. Asia is 60% of emissions. That's where there should be much more activities. So I think I'm sure that Europe is well off here. We can manage that. But now on the global side, there's too little R&D in emerging economies, actually on energy, to cope with their questions there. On other, let's say, even though let's say the money is there and should be okay, but there's also some dark clouds in the horizon. And it's really on the corporate funding. We're seeing already that corporate R&D is starting to erode because of the inflation and because of the high interest rate. And that's where the public sector institutions may need to give a push that the corporate funding in R&D stays good, because otherwise we won't get technologies on the market. We may get a lot of research results and scientific papers, but we don't get the technologies on the market. So for upscaling, for instance, now that is in risk, that there's not enough kind of a funding to do the R&D for that side. So there's a range of challenges that the energy transition brings in technology-wise, and clear trends and challenges in the sense that, for instance, electric technologies will be very important. Fuels is something that we need definitely in the future, but electricity will increase its role. When we speak about electric system, it's much more complex. It's a very complex system, and in that sense will need new skills, which skills necessarily would not be there. We have been talking also very much in this conference about scaling up. Scaling up is definitely the requirement for the energy transition. You may have good technologies, but if they don't match the size and the scale of energy, is in vain. So scaling up is something that we should keep definitely in mind. And another important issue is also infrastructure. If we don't have adequate infrastructure, but we have enough solar and wind, I mean, you can't use those. So infrastructures, by and large, even logistics and grids and so on, would be extremely important from the technology point of view as well. Now, in order to understand slightly better the different challenges that we have with the different technologies and the opportunities, let's just very quickly look how the energy system works and look at the energy framework. I'm simplifying here very much, but basically energy system is about demand and about supply. That's an economy, economic terms in a way. And your needs, our needs, they define the demand, and then we have the energy system, which is quite complex on the bottom here, will deliver you the supply. So your needs, our needs, the industrial needs, they define the demand, which is then supplied by the energy system, where we then get the CO2 emissions. Looking on the gap between demand and supply. So we have the demand, which goes as signal to the supply. So when we start to look on the supply system, it has many stages. There's a lot of conversion stages before the raw material of energy turns into usable services that you need in your homes or in offices, in industries. And these steps, each of these steps have major actually losses. So much of the energy that we produce actually is lost, and there's no use of that. That's why energy efficiency, energy savings, in particular close to the energy demand side, will be important. Because what happens if I would be able to save in the demand? The good things goes through the whole energy delivery chain. It means I need less infrastructure, I need less cables, less transmission, less power plants, less fuels, less mining, less critical materials. Everything is diminished. So if I would do my job on the energy demand side correctly, reduce the demand, as now the Energy Efficiency Directive will say, let's do it by 2050. Each year, let's say 0.5% improvement at least. We would actually say tens of percents in the supply, maybe in some countries up to 50%. So you need just half of the wind or solar to produce the same energy service that you need. That's why, as I said before, the Commission says energy efficiency first. It's the cheapest energy, and it has the best benefits, and it has a lot of positive effects on the energy transition that we have. Energy transition without energy efficiency, I don't believe that it works. I mean, we need so much materials. Already now, when we look on the amount of copper just for the cables, not just for the technology, just for the cables that we need, that amounts the copper demand that we have had over the last 70 years. So that's not enough. So that's why we need to be efficient. As we are efficient with using money, let's be efficient in using energy. And we have good examples for many countries that this is manageable, though what is important to say, very often energy efficiency also incorporates behavioral effects. Behavior has to change. It's not just a technology question. So that's the energy demand side, and hopefully we can, as said, reduce there. There's a lot of good technologies, as we have heard already today. On that side, heat pumps, for instance, energy efficient appliances, you name it. So there's also technologies that can help us. Now, moving to the supply side, the options that we have there are about the option for 2050 are about those that we have. There may come surprises that we have heard, and I have a few jokers here also. But most likely, those technologies that you see here are what we have. We have the traditional fossil fuels. So if we use fossil fuels in the future, we need to take the carbon, manage that, and store that or reuse. So carbon management and fossil fuels, that is a must in the future. In case of bioenergy, which is also a combustion technology, produces CO2, we often say that bioenergy, well, the trees takes and plants the CO2 back. So we have a carbon circulation. Now, depending on what kind of biomass you have, it may be the circulation takes 60 years, 70 years, like the Finnish forest, and most likely would need also carbon management for those type of biomasses. If you have very quick-growing crops, that would not be a problem. So carbon capture and storage and utilization, that would be something that we need to look really definitely on technologies that emit CO2, being bioenergy most likely, but in any way on fossil fuel. Then we have a range of electric technologies which are CO2-free. Old renewables like hydropower, we heard about that. There's a lot of potential here, of course, in the surroundings. Then we have new renewables, mainly solar and wind. Those are the two technologies that grow. And then we have, of course, nuclear power, which is more traditional energy. And now, let's look in the future. This is what our friend Michael, he thought that it would be interesting to see where could we go with electric production supply technologies. So let's say that research is successful. Where could that bring? So we have definitely an energy dream, which is a fusion. Power plants which work with water. I mean, this is not a joke. Fusion power works with water. 1 liter of water is 300 liter equivalent oil. And that's why in Hollywood films, actually, if you remember this DeLorean by Emmett Brown, he was the Back to the Future inventor. He had fusion power in his car and used water for that. It was not a joke in the sense that, yes, water has hydrogen, and in hydrogen we have 2 isotopes which are important for fusion. So let's take a short physics lesson in fusion. How does it work? I know economists hate physics. I'm a physicist. I know that. They hate that. But now let's just concentrate, and I think we managed it. So fusion is about very, let's say, the lightest nuclei we have, which is hydrogen. Hydrogen has 3 isotopes. The ordinary hydrogen, then we have deuterium. That's 1 neutron more. That's too difficult. But anyway, it's heavier. And then we have tritium, which is more heavier. Take the deuterium and tritium. Let's put it together, and then let's heat up it. Now comes quite interesting. We heat up to 150 million degrees. And that's a challenge because the sun is just 10 million, so we go to 10 suns. Heat up, then of course the atoms become ionized atoms, and everything is a plasma. That's a plasma ball you have seen maybe in James Bond, you see the plasma. And then you need to confine that. Have a magnet or laser. You see on the bottom some of the technologies, and you confine it, make it very dense, and boom, then we have the fusion reaction. And that causes a lot of energy. And indeed, with just those 2 isotopes, which are in water, you really get a lot of energy out of the reaction. Of course, this is very challenging. I mean, keep in some way intact the plasma. We will see in a while how challenging that is. But the benefit with the fusion is that instead of a fission which has a lot of radiotoxicity for thousands of years, the fusion, the radiotoxicity which comes from the neutron. The neutron is the one which hits the wall of the fusion reactor, and it makes the walls slightly radioactive. So we have to wait for 100 years. 100 years, then the radioactivity have decayed away. So no waste. So what you have is water and a black box, and you get energy, and then you keep the waste for 100 years. So it's the ideal final solution, I would say, for sure. So now the question is that what do we need to do here in order to have the fusion working? And that's where we need to really confine the plasma. So first heat up it, confine, and then of course you have to keep it there, time-wise. I mean, if it just bumps it away, nothing happens. So you have to keep it for a certain time. And those 3 factors, density, temperature, and the confinement time, that is the critical so-called triple product, which needs to exceed a certain threshold level. And here you see on the right-hand side where we are not yet there, but with the ITER reactor, the European Initiative in Fusion, we are very close to that. So it should demonstrate that. So you see here the landmark experiments, the big ITER. These are quite complicated devices. ITER is a big magnet which really keeps with magnets the plasma together and really compacts it, and it should produce 10 times more heat or energy than you put in. Then we had the laser system, which is on the right-hand side, which the US researchers have used. And last December, there was a lot of news about fusion, that yes, there's a breakthrough, and lead in terms of the of the fusion reaction, which in this case is really handled in the way that we have a small pellet of deuterium and tritium and 2 very powerful lasers that shoot on that. And that causes really such a confinement. Temperature goes to 100, 150 million degrees, and you have very dense plasma, and the fusion reaction starts. They got 50% more energy than they put in the reaction. Now, there's a small caveat. They forgot to tell that the lasers needed 100 times more energy. So if you account for that, we are still a way off. But a breakthrough in terms of the fusion reaction, but not a breakthrough in technology. And the breakthrough of the technology, that's something that we expect that will come through the experiments and most likely toward the end of this century. That's the timeline where we expect that the commercial fusion reactors working with water, so to say, would be there and useful. An important maybe change in the fusion research. The fusion research is really big science. One experiment, 20 million euros, all right, and it's really expensive. And I think there's now changing the research in the sense that we expect that linking private industries more with the fusion research may bring the scientists and the entrepreneurs who can make workable technologies together. We've seen that in space industries. Bringing SpaceX into NASA made it possible to really create super technologies for spacecraft, reusing the rockets, etc. The same thing should happen most likely in fusion. So just going with the scientists, big science, most likely will be a very, very long way. And having the private sector also involved may speed it up. Now going to another fusion technology that works with fusion is renewable energy. Now you ask, how is that? Where's the deuterium? Well, the deuterium is in the sun. Sun is a fusion reactor. And in a way, that's the working reactor. And of course, renewable energy is energy from the sun, which converts itself into hydropower or in direct solar or in the wind power. And here we have seen tremendous improvements in the last years. In the figure you see on the upper part of the curves, the price decline over years, a huge price decline during the last 10 years in solar, wind, and also in batteries, which leads to penetration, which is the bottom line here. And that has actually caused the breakthrough of these technologies. We are on par with and even below the cost of traditional energy. So the scaling up has succeeded, but here again, it's the industries, not the researchers. So when you have the industries coming in with their knowledge, and in particular now, in this case, also the Chinese, who are able to scale in big scale. In China, you have to think always on 1.5 billion people, so scaling up, how you scale is a talent which has also come into this picture. There's also factors that may limit now the growth of the new renewables, and in particular the land use. As you know, the panels need a lot of land, and wind need a lot of land. About 10 times more land area than an ordinary power plant that we have. So land use may be starting to be a restricting factor. So we need to think about land use, using arid areas or other built environment areas. Also, permitting is very slow, which slows down now. Maybe the pace in the future need to be much quicker, and also the infrastructure, grid infrastructure. In US, there's about 22,000 gigawatts of solar and wind waiting to be connected to the grid. That's a huge amount, and would correspond to a major part of electricity in most of the European countries. Critical materials is of course, a question that was also raised today. And indeed, if we don't do anything, there will be huge bottlenecks in achieving materials for these new technologies. Having said that, there's solutions also. We need to look on recycling. We are not recycling enough the materials, clearly a very easy way, and also replacing materials. We don't need to use all the materials that we have. There's other replacements and improving efficiency, etc. So there's a way to get around that technology bottleneck that may appear, but you need to be conscious about that. All right, so I need to now maybe slightly speed up the technologies. We spent too much with the fusion, but let me point out that now the flexibility technologies, which we spoke already early on, will be very, very important. Extremely important with these new technologies which are varying with the weather. So to make solar and wind like fuel, you have to add these flexibility technologies, which you see there on the right-hand side, a mix of those. Which mix? Well, it depends on your local conditions, which again needs skill. So the way we plan our energy system is quite different. Have we fuel or do we have solar and wind? Solar and wind alone doesn't work good enough. So you need, let me point out, these flexibility technologies, which may be energy storage, which may be demand side management, digitalization, etc. A lot of technologies here again. Or batteries. Now we used to speak about lithium-ion batteries. That's the technology. And we know that lithium-ion batteries have critical materials, lithium, nickel, cobalt. Not enough, and very expensive. We have a breakthrough now coming in the batteries, going to sodium-ion batteries, replacing all these precious materials with table salt. Well, sodium is table salt. And we have the first prototypes. These are to Chinese manufacturers. I would have hoped that it's European ones, but there's Chinese first kind of workable sodium-ion battery. Well, the material cost is just 1/20th of the lithium-ion battery. It takes some time to make this a good product, but once this is, you have a full breakthrough in batteries, cheap batteries, for stationary application or for mobile activities. Sure, Europe should invest much more in batteries. We are actually lacking very much China and US in this field. Hydrogen, that is coming. Hydrogen, during this decade, we estimate that will be commercial. And indeed, we have heard today about the US IRA program, which subsidizes green hydrogen for solar and wind in a way that is competitive with hydrogen from natural gas. From $5 to $2 per kilogram hydrogen, that's subsidized. So US companies using green hydrogen hugely now, which opens up the market and will most likely bring the price down. This may be one of the final solutions that we need in the energy system, but again, after 2030. Nuclear power is of course a option as well. The present nuclear power has problems in the sense that it's too costly and takes too long time. And we see that the volume has stagnated. Future, maybe in small modular reactors, there's opportunities in scaling, in mass production, but there's challenges as well. And the main challenge, what I would say, is again economics. You need to look on the economics. And this is a challenge in this technology. We have a lot of startups which may not be that critical with the economy if you have subsidies. If everything goes well, these reactors could replace about a quarter of all reactors by 2050. So old reactors dropping off could be replaced by this technology, but you need to address these challenges. I'll skip the carbon technology and come to my joker, which is digitalization. Let me just say that what we will see in digitalization is something that you can't realize. Quantum computers, some of my colleagues work on those globally. Quantum computers which are a million times more powerful as your computers. Machine learning with new algorithms and 6G transmission communication, which is super fast. We can go as Dr. Emmett went in the Back to the Future, have a digital twin, do things there, maybe respond to some forecast errors, etc. And in that digital twin, then we come back to the real thing and fix the things in the real system. So the digital virtual world is where we can really do real things in the future and come back to the present situation. That will open up huge opportunities to govern very complex energy systems that will have huge opportunities in the material side. Machine learning, when it's good, is the tool which starts when science stops. Science stops at some point. Science doesn't explain. That's where you put the black box with machine learning. You get new materials. Already in batteries, we get materials we never thought about that working. And that will be a very powerful tool also to create new technologies. This is maybe one of the most important research tools in the future. So ladies and gentlemen, time is off, and let me just come to my last slide. My conclusions would be, of course, that yes, we have a lot of options there. and new options inside as part of the evolution. I believe in evolution, and I think most of you do as well, and I believe in technology evolution. And so as long as there's ingenuity, we have new technologies, and we saw already a few that comes behind the corner. Now the stone men from the Stone Age, as you see there, we are not sure did they believe on innovations. They were they were too busy, as you see. Most of us are too busy. But empirical observations of the Stone Age over 10,000 years shows that actually the Stone Age didn't cease because these guys would have run out of stones. No. Somebody believed in innovation. And the innovation, that was the key that we jumped from Stone Age then to modern time. In the same way, the fossil fuels. The use of fossil fuels doesn't stop, that we run out of fossil fuels. But it's because we have new innovations that provide better solutions. So innovation is a key for the change that we have. And hopefully we can endorse that adequately. So ladies and gentlemen, with these words, I thank you very much for your attention. Thank you.